Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the common ion effect. I am sure you recall that in our last lesson, we learned about the Lewis concept of acids and bases. We learned that according to Lewis's concept, an acid is a substance that can form a coordinate covalent bond by accepting an electron pair from another substance. A base is a substance that is capable of donating a pair of electrons. We learned that the Lewis concept includes both the Arrhenius and the Bronsted-Lowry, but also expands upon them. The Lewis concept includes ions or molecules that are able to accept an electron pair that neither release a proton in aqueous solution nor donate a proton. In today's lesson, we will define the common ion effect. We will also explain the importance of common ions and show some effects of common ions and the process. We will learn how to apply Le Chateliers Principle, which we have learned about in previous lessons. Students, if you are prepared, then we will get started. The common ion effect is an effect that occurs when two substances which both ionize to produce the same common ion are involved in chemical equilibrium. In other words, it is caused by the addition of a compound that has an ion in common with the dissolved substance, which shifts the equilibrium. When a common ion is present, it suppresses the ionization of a weak acid or a weak base. Students, shall we look at an example? If sodium acetate and acetic acid are dissolved in the same solution, they both dissociate and ionize to give acetate ions. Sodium acetate is a strong electrolyte. Thus, it dissociates completely when it is put into solution. Acetic acid, on the other hand, is a weak acid. It only ionizes partially. Students, let us do a review. Can you recall what Le Chateliers Principle is? Please describe it now. After we take up this activity, I will show you how this principle applies to our current lesson.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I am sure that you had no trouble recalling Le Chatelier's principle. This principle states that if a chemical system is at equilibrium and it experiences a change in concentration, temperature, volume, or partial pressure, then the equilibrium shifts. It does so in order to counteract the change that has been imposed upon it. This results in the establishment of a new equilibrium. Is that how you described Le Chatelier's principle? If so, well done. Now, let us apply it to this lesson. According to Le Chatelier's principle, when the acetate ions are added from the sodium acetate to a solution of acetic acid, the ionization of the acetic acid will be suppressed. This will decrease the concentration of hydrogen ions. Therefore, if we have a solution that contains both acetic acid and sodium acetate, it will be less acidic than a solution that only contains acetic acid of the same concentration. A shift in equilibrium that suppresses the ionization of the acetic acid occurs because of the acetate ions from the sodium acetate. Acetate ion is considered the common ion because it is supplied by both acetic acid and sodium acetate. Students, let us try an activity. Determine the hydronium concentration and acetate concentration in a solution that is 0.10 molar in both acetic acid and hydrochloric acid.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, everyone. How did you do? We know that 0.10 molar of hydrochloric acid ionizes completely to form 0.10 molar of hydronium and 0.10 molar of chloride ions. The chloride ion is a spectator ion. Thus, it has no influence on the concentration of acetate and hydronium. The initial concentration of acetic acid is 0.10 molar. The initial concentration of acetate ion is 0.0 molar. And the initial concentration of hydronium ion is 0.10 molar. The change and equilibrium shifts that occur are as you see here. Therefore, the acid dissociation constant of acetic acid is equal to the equilibrium concentration of hydronium ion times the equilibrium concentration of acetate ion divided by the equilibrium concentration of acetic acid. We know that the acid dissociation constant of acetic acid is equal to 1.8 times 10 to the power of negative 5. Therefore, we get 1.8 times 10 to the power of negative 5 equals 0.10 plus x, all times x, all divided by 0.10 minus x. If x is very small, then we can approximate 0.10 minus x and 0.10 plus x to 0.10. This gives us the following answer. If you are having trouble with this, please ask your teacher for assistance at the end of the lesson. In today's lesson, we learned about the common ion effect. We learned that it is an effect that occurs when two substances, which both ionize to produce the same common ion, are involved in chemical equilibrium. We learned how this effect relates to Le Chatelier's principle, and we discussed the effects of some common ions. This brings us to the end of our lesson for today. Until next time, thank you, teacher. Thank you, students.